slide here, we'll be looking at the constant pressure cycle. We'll be looking at the constant pressure cycle. Okay. So now for constant pressure cycle, we will have two reversible constant pressure processes and two reversible isentropic processes. Two reversible constant pressure processes and two reversible isentropic or adiabatic processes. Or we can draw a schematic diagram for the closed gas turbine unit. The constant pressure cycle sometimes is known as closed gas turbine unit. So it consists of a compressor which helps to circulate the air in the cycle. And then you have a heat exchanger, that means a heater to supply heat to the air. Then you have a turbine which extract work from the system, that means the air. Then you have a cooler that functions as, okay, rejecting the heat if it is not, or it is unavailable energy, or it is not converted to useful work. Okay, the remaining energy that is in the air will have to be rejected. So by means of the cooler here, both the heater and the cooler are called heat exchangers. Heater is to supply heat to the air. Cooler is to remove heat energy, that means unwanted heat energy from the system. Compressor, you have the work input. Turbine, you have the work output. So turbine usually is used to extract work. That means to convert any heat energy to useful work. So the whole process here runs at a constant pressure. They run at constant pressure processes. Like the heater and the cooler, they undergoes constant pressure process. Like the compressor and the turbine, they goes under adiabatic or isentropic process. So based on this, you can see, okay, it actually move in a clockwise manner, okay, clockwise direction. So first air is being sucked to the compressor. That means the compressor take in air from the surroundings. And then after that, it undergoes isentropic compressions. Okay, the air will undergo isentropic or adiabatic compression and then send it to the heater where heat is supplied to the air. Okay, so the heater operates under a constant pressure process. Then after that, the hot air will now then enter the turbine. And in the turbine, it will undergo isentropic expansion. In the heater just now, it will undergo a constant pressure heating. In the turbine, it will undergo isentropic or adiabatic expansion. Then it will be, after that, a certain amount of work or a very low percentage of the heat energy that is in the air will be converted to useful work like, okay, generating power or moving a propeller or and etc. etc. So after undergoing isentropic expansion, those energy which cannot be converted to useful work will have to be rejected to a lower temperature region. So that is why it enters a cooler and it undergoes constant pressure cooling. Then it goes back to the compressor again, where it undergoes a full cycle. Okay, so on the PV and TS diagram, okay, later on we will go into the PV diagram yeah. Now, what is a closed gas turbine unit? Now, the open gas turbine cycle, now you have a closed gas turbine unit and an open gas turbine unit actually. We'll go into the open gas turbine unit in the later stage. Now can be remodeled as a closed cycle by utilizing the A standard assumptions. Okay, now the compression and expansion remains the same. The combustion process is replaced by a constant pressure heater or heating process. Okay, so by some external source. and the exhaust process is replaced, the exhaust process here, okay, is replaced by a constant pressure heat rejection process by a cooler. Okay, the ideal cycle that's working, that the working fluid undergoes in this closed loop, this is called a closed loop. Later on, you will have an open gas turbine unit. Okay, it's called a Brayton cycle, or a constant pressure cycle. Okay, or a Brayton cycle. This is your TS diagram. So on the TS diagram, you can see from point 1 to 2, that is the compressor, it undergoes an isentropic compression. Isentropic means the constant entropy. So from here, you can see S1 is equals to S2. Okay, so constant entropy. And then when you look at the temperature, it actually increases from state point 1 to state point 2. So is isentropic compression. So the temperature increase, so do the pressure. The pressure will also increase. Then from state point 2 to state point 3, okay, the air will goes into a heater now, where you have heat addition into the system or the air. So it undergoes a constant pressure process. So from state point 2 to state point 3, you can see, okay, that this process here is a constant pressure line. Okay, so you have heat addition, because in the direction from point 2 to point 3 is the increasing entropy as you measure from the point of origin here. Towards this direction is actually the increasing entropy. So increasing entropy, that means you have heat supply. Then you have isentropic expansion from state point 3 to 4. Then it goes back to constant pressure process from point 4 to state point 4 to state point 1, where heat is rejected. That is when it undergoes a constant pressure cooling process. So basically, this is your TS diagram. So TS diagram, basically, you can look into the area S for heat flow. So for PV is work done. Okay. So isentropic compression, then constant pressure heating, then isentropic expansion, then you have constant pressure cooling. Okay, so for a gas turbine power cycle or constant pressure cycle or Brayton cycle, so based on steady flow energy equation, if you are taking based on steady flow energy equation, first you look at the gas turbine. So this is the gas turbine. So by looking at the steady flow energy equation, so that is the difference between the heat and the work from state point 3 to 4. So this is the specific potential energy change, and this is the specific kinetic energy change, and this gives you the enthalpy change. So basically, when you refer to a turbine, okay, the changes in potential and the changes in kinetic energy, they are neglected because they are too small as compared to the heat, work, and the change of enthalpy. Now, but in turbine, since it's an isentropic process, so the heat here, the Q34 is 0. So the potential, the specific potential energy change also will be neglected. The specific kinetic energy change also will be neglected. So what is remain is your work from 3 to 4 with the change of enthalpy. So isentropic expansion is isentropic expansion here. So the Q is 0. That means no heat flow. Okay, and negligible changes in potential energy. And then you have negligible changes in kinetic energy. Then what is remain is your work from 3 to 4. Okay, negative W34 equals to H4 minus H3. So if you were to manipulate the equation here, the negative sign here, it changes H3 and H4. So this will give you the work output from the constant pressure cycle. This will give you the work output based on the constant pressure cycle. So if let's say, for example, it refers to the H is enthalpy, U is internal energy. So we know that internal energy U is equals to CVT, H is equals to CPT. So you can find out your work output in terms of enthalpy or you can also find out your work output in terms of Cp T3 minus T4, because we know that H is equal to Cpt if you were to refer back to your previous studies. So the Cp here, the specific heat capacity at constant pressure, Cp refers to specific heat capacity at constant pressure. Now the system that we are looking at is A. So that is why you look at CPA. So CBA standard is 1.005. So and then the temperature here is in Kelvin. Okay. So that is based on the turbine, based on steady flow energy equation. So and then the isentropic compression for the compressor. So you have again the steady flow energy equation, again QW, but this time we are referring to state point 1 to 2, the heat and the work, and this is a specific change in potential energy, and then this is a specific change in kinetic energy, and this is the enthalpy. Now we say specific, specific, that means it should be in kilojoules per kg, and this also in kilojoules per kg. If let's say you have mg, you have m and m beside the g and the m besides the c here. The c here stands for velocity, C here stands for velocity. Then if you have m and m here, then it is called absolute. So if you, let's say for example, the m doesn't appear here, that means these two terms here is also considered as specific. So you have specific heat, specific work, specific potential energy change, specific kinetic energy change, and specific enthalpy change. So for compressor, potential energy and specific kinetic energy both are again neglected. If you were to refer back to your steady flow devices. Steady flow devices, usually compressor and turbine, we neglect the specific change in potential and the specific change in kinetic energy. And then also the heat, because if let's say we assume that is isentropic or adiabatic, then the Q will be neglected. So what is left is the work with the change of enthalpy. So these are the reasons, or these are the analysis of compressor. So what you have is this as the work input. So you can express work input as the change of enthalpy, or you can represent it in terms of Cp. Again, is CPA, Since at the earlier stage, the intake is A, outlet is A. For the turbine, intake is A, outlet is also A. If let's say when you are referring to an open unit, then on the gas side is not A, it will be some hot gases. So this is the work input and this is the work output. So now the next one is actually the heater and the cooler. So if you want to find the heat supply and the heat rejected, you can say the heat supply here is also Cp T3 minus T2. And then the heat rejected here to be Cp T4 minus T1. T4 minus T1 here, you have T3 minus T2. Heat supply and heat rejected. So this is your constant pressure cycle, PV and TS. So now we know that constant pressure cycle consists of two constant pressure process. So that is why you can see I've drawn here two horizontal lines. And then on the TS diagram, we know that the constant pressure process will appear as a curve or a line like this, which as compares to the temperature line, as compares to the volume line, the pressure line is less steep. For volume line is steeper. So if you still remember what I have taught you, on the previous podcast video slides. So you have these both as the constant pressure line. Now remember, constant pressure process consists of two constant pressure processes and two isentropic processes. So 1 to 2 here is an isentropic process. 3 to 4 is also isentropic process. So it appears as a curve like that. So if you want to draw a constant pressure cycle on the PV diagram, make sure you draw two constant pressure line, horizontal line across, and then to both the curves like this. Okay, so it closes up and it forms a cycle. So we have 1, 2, 3, and 4 state points. So it flows from 1 to 2, 2 to 3, 3 to 4, and 4 to 1 in clockwise direction. Okay, so remember, if let's say, for example, you want to find work done, you can also refer to PV diagram. If you want to find heat flow, you can refer to the TS diagram in case you are referring to internal reversible. Okay, internal reversible process. So now for the heater and the cooler, okay, so the constant pressure heat addition, again, you refers to the steady flow. Now this time you cannot neglect the heat because you see it's heat addition. Heat addition, that means the heat must be included. The only thing we neglect is the work, because the work, okay, the heater and the cooler doesn't require a shaft, so that is why it neglects later on. The change in potential and kinetic energy also will be neglected. So the heat will only be equals to the change of enthalpy if we are referring to steady flow. So the work will be 0. The specific potential energy change 0. Specific kinetic energy change is 0. What is left over is the Q and the H only. So you can find out heat supply. This is heat supply. Yeah? 2 to 3 is heat supply because it is in the increasing entropy direction. So you have heat supply, H2 minus H3. Okay, so or you can change this to CPAT. So you have CPA T3 minus T2. That is for the heater or the heat supply. Then based on steady flow, again for the cooler, 4 to 1. Constant pressure heat rejection, the heat exchanger, that means that is the cooler, the device that we use is cooler, and this is heater. From external source, the heat is supplied from an external source. The cooler is when the heat is rejected to outside. So heat, work, potential, kinetic, and enthalpy change. So again, there's no work, so we neglect. Potential, kinetic, all neglected. So what is left over later on will be equals to the change of enthalpy only. Okay, so or you can replace it with CPT. Remember, H can be replaced by CP, pressure, T. C is specific capacity. With the subscript P, that means it's constant pressure. With subscript V, that means it's constant volume. CVT is U. CVT is U. CPT is H. Okay, how to get CPT or CVT? Then we have to look into the general relationship of thermodynamics properties. Okay, in the later stage. So we know that, okay, net work out, I think by now you know net work out is actually equals to heat supply minus heat rejected. So it can also be equals to work out minus work in. Okay, so the work out is CPA, not CPG. T3 minus T4. Okay, work in is CPA T2 minus T1. Unless if you are referring to an open cycle, then you can put here, you have to put here as gas. And then the inlet as air, the outlet as gas. But then we will go to that in the later stage. So you can either express your net work out as heat supply minus heat reject. You can express net work out as heat supply minus heat rejected, or work out minus work in. So the work out is the work by the turbine. Work in is the work done on the system in the compressor. Okay, this is heat supply and this is heat rejected is not written here. So your cycle efficiency or the thermal efficiency or cycle efficiency for any cycles is defined as desired output over required input. The desired output for heat engine cycles is always the net work out. The required input is always the heat supply. Okay, and then work ratio is another term which is defined as net work out over gross work expansion. Later on in the examples of problem solving, I will teach you how to find out this gross work expansion. So if let's say you want to find out net power output, usually you have to take network out times mass flow rate. This is called mass flow rate, which is in kg per second. Okay, thank you.